Hi, my name is David, and I try to play guitar. I'm not very good, as you can tell. One day, I saw a video of blues great Joe Bonamassa getting very technical about his guitar amplifiers. For a guitar player, that guy really knows his stuff about amps. He inspired me to learn more. But to really understand guitar amps, you need to take them apart and put them back together. I watched hundreds of videos. I read all kinds of books. From Craigslist and eBay, I bought a used soldering iron, some old voltmeters, an ancient oscilloscope, and other test gear. Eventually, I built an entire electronics lab. Now, I guess I'm sort of an amp mechanic. I fix other electronics too, and this is my journey. I figured I'd share so others can learn too. I hope you like it, and just as a disclaimer, be sure to consult an expert before working with electricity.
Hey everybody out there on YouTube, Dave the Amp Mechanic coming to you from Boston, Massachusetts. I'm down here in the Amp Lab. I've got another great video for you today. Today we're going to talk about something called an Opto-Coupler. It's a little bit of solid-state technology that you might sometimes find in a newer amplifier. Now what I mean by newer, it's not one of the old vintage amps from the 60s that have no solid-state technology in them. Now why would I bother even talking about some of these newer amps, or fixing one for that matter? Well, when I first broke into fixing amplifiers, the luthier that works on my guitars said, "Here, this amp makes no sound at all, see if you can get it working." And I thought, great, I've got my first amp to work on. Well, when I opened that amp up, I discovered that it was more of a hybrid amp. It was this vintage stuff. It's got tubes, it's got capacitors and resistors, but it also had some new technology in it, some solid state stuff. I thought, oh no, it's like the worst possible thing that anybody getting started on fixing amps could start to work with. An amplifier that has solid state technology. I know nothing about solid state, and well, I guess I just had to figure it out, because you never know if maybe that's what's preventing the amp from working. In fact, in a lot of cases, the solid state technology is far less durable than the older vintage tech, and it could easily melt down, blow up in a way that prevents an amplifier from working. So when I opened this amplifier up, I discovered these small little opto-couplers, 5 of them, and I was wondering what they did, how they worked, and whether or not they could be the reason or the source of the trouble in this amplifier. I had to figure that out. And I also had to make a clever little device to test them with. So let's get started. You're going to find out what an opto-coupler does, how it works, and what role it played in this amplifier. Okay, so we're looking at the circuit board of the Crate Vintage Club 30 amplifier. It's in its chassis, and the chassis right now is sitting on my amp cradle, which is sitting on my bench. So the chassis is not in the cabinet that it came in. The cabinet's sitting over somewhere else in my lab. And then when you look at this, you can see some of the technology that you might find in older vintage amplifiers, ones that don't have any solid state technology. So for example, you see, like, we've got sockets, tube sockets. There's 8 tubes in this amp, 4 12AX7s that are used for the preamp section, and then over here you've got EL84s that are your output tubes. Now the tubes are on the other side. This is the top side, or actually the bottom side, quite frankly, of the socket. We're looking straight down into the tube right now, and in fact, one of the cool things about these sockets is that you can see, if you look closely, you can see little metal tabs in them, and those tabs are really perfect for probing with multimeters and with your oscilloscope, just to see what's going on each of the pins of the tubes. The sockets are numbered nicely, with the pin number that we're talking about on the tube that's underneath it. So when I started working on this amplifier, I noticed that it had a bunch of solid-state technology in it. 5 pieces of solid-state technology in particular that caught my eye were these devices right here, right? And they're called opto-couplers, or Vactrols, right? And I had no idea what they did or if they played any role in the problem that this amplifier was having. But what I did know was that the old capacitors, the old electrolytics, and we're talking about these guys right here, they were showing signs of heat stress. So an example would be this particular one here, which I pulled out of this amp, and you can see that the top is domed right there, right? You see that's kind of like a dome top. And the top itself is really just a cover. There's no other functional aspect of that top, but the fact that it's domed suggests that this capacitor got very, very hot and suffered some form of heat stress. Now, that doesn't mean the capacitor failed, but I wanted to replace them anyway, just in case they were worn out. And in the video that I made for this particular amplifier, we'll talk more about these particular capacitors and what the trouble was with them. But knowing that this amplifier got so hot caused me to wonder whether or not some of the solid state technology in here also failed as a result of that heat. One problem with all that heat is that if their circuits are overloaded, for example, if there's too much current going through a circuit, these guys are made to a certain specification and can't really stand up to that kind of stress. There's a chance or a possibility that they just fried completely. And I wasn't sure even if that mattered or not. Let's say one of these devices fried. Would it actually keep the amp from working altogether? I wasn't sure. So I started poking around on the web to figure out what these Vactrols or Opto-Couplers did. And then I turned to the schematic of this amp, which tells the total story of what their role is and whether or not the problem could be traced back to a failing Opto-Coupler. So let's turn to the schematic so you get an idea of what they do, how they work, and whether or not they might have a role in the malfunctioning of this amplifier. Okay, so here we're looking at the schematic of the Crate Vintage Club 30. I apologize for all the notations on it. Some of these are related to observations I was making as I was fixing the amp itself. But what's most important for this particular video is to note where the opto-couplers are, and then from there to figure out what their role is in operating this amplifier. So if you look closely at this circuit diagram, what we have are 5 opto-couplers, and this is where they appear. Here's the first one. It's labeled OC1, and then here's the second one, OC2, OC3, OC4, and OC5. So you can see that they're sprinkled into 2 circuits here. One is the clean channel of the amplifier. The other one is the dirty channel. So here's the clean channel right here, and here is the dirty channel right here. Clean, of course, being very clean sound. Dirty is the one that has the distortion, more of a rock sound if you want to call it that, right? And you can see how the circuits operate. Here's the tone stack right in here for the circuit. Here are the tubes. For example, here are the preamp tubes. The very first tube right here, the first half of the 12AX7, the signal comes in through the jack into the grid of the 12AX7, and then it goes through the clean circuit. And down here, which was really important to me, is the switching mechanism for the clean and dirty switch, because I wasn't sure if that mechanism was even working or not. At one point, I was just getting sound out of the dirty channel and it wasn't switching to the clean channel at all. And so I was very concerned about whether or not the switch was functioning, whether the foot switch jack was busted. I wasn't exactly sure what exactly the problem was. But I saw these opto-couplers sprinkled throughout the circuit and began to wonder, could that be the problem? And so to sort of understand exactly what these opto-couplers do, first I studied some documentation that I found on the web, and it was pretty interesting how they work. If you look very closely, let's take, for example, this one here, OC4, you can see that it looks like an opto-coupler has 2 parts to it. One of them is a diode, and the other one is a resistor, right? And each one of them is the same. Now, they're positioned at different parts of the circuit, and they're even positioned in different directions. But in general, I was trying to figure out, well, what do these do? Why do they have these two components inside of them? And as it turns out, very interestingly, what they do is they work in a way that if this diode, which is actually an LED, this diode illuminates, it reduces the resistance in the resistor. It's really cool if you ask me. I mean, like, that is a really neat piece of technology. So in other words, if you are putting voltage onto the circuit, onto this part of the circuit that has the diode and the LED in it, then you're reducing the resistance here. And that's the same of all of these. And so I thought, wow, that's kind of neat. Why would they do that? Well, it's pretty simple. When you put the amplifier into the clean mode, what it does is it makes sure that these different opto-couplers that are in the dirty circuit are off. In other words, the LEDs are dark. And when the LEDs are dark, it increases the resistance so that the signal cannot flow through the dirty circuit and find its way all the way out over here, which is to the rest of the amplifier. In contrast, when you want dirty sound, you want to use channel B, you push the button in on the clean dirty switch, the channel selector switch on the front of the amplifier, and what it does is it turns off the LEDs that are in circuit on the clean channel, and thereby increasing the resistance here, and it turns on the opto-coupler LEDs in the dirty channel. In other words, it reduces the resistance, and that allows the signal to pass through that circuit. So how cool is that? That is the difference between old vintage technology and newer technology, is that they can accomplish some of the same things with much smaller, much more miniaturized parts like these opto-couplers that are essentially performing like gates. They're logical in their function. And for me personally, as an old software developer, I find this fascinating because basically what you're doing is you're just basically turning on one circuit and turning off another circuit. This is exactly the way computers work. It's a bunch of ones and zeros. One means on, zero means off. And so what we're really doing is we're basically applying the same logic here. If we want the clean channel on, we turn on, we set these to 1 essentially. We turn on these opto-coupler LEDs. If we want these opto-couplers on, then we turn those ones on and the other ones off. They set them to dark. Okay, let's take a look at the workflow of this circuit just to get an idea of how these opto-couplers work. First, let's look at the signal coming in from the guitar. This is the jack, the input jack right over here, and you've got a signal that comes in, and the very first thing it does is it hits the grid of the first preamp tube, which is a 12AX7. So here's the grid, signal comes in here, and then it goes up to the plate of that tube. This is, by the way, the first half of the first tube. Is 12AX7s essentially perform like two tubes in one. It goes up to the plate, and then it starts heading down this path over here. And we've got a coupling capacitor here that prevents this DC coming in from the B+, the high voltage, from heading down to the next part of the circuit where it's going to go through another grid, which is over here. We don't want DC on that grid. So that's a coupling capacitor. But you can see that the signal kind of moves down this way, and look at that. It goes right through one of these opto-couplers. So you can imagine that if the clean circuit were off and the dirty circuit was on, in other words, this LED was off and this resistance was set to high as a result of this being off, that the signal would be prevented from going any further. And that is exactly how the opto-coupler works. I mean, that's, to me, is just fascinating, because in the old days, the way you would have done this is with some physical switching mechanism. They're doing it with solid-state technologies, LEDs, and resistors. It's just amazing how these things work, and I started thinking, boy, what else could I use an opto-coupler for in something else that I might want to build in the future? Because I'm definitely going to try them out. So the signal goes through here. Now let's say this LED is on. It goes through here. It goes through the tone stack. You can see here's the treble potentiometer. Here's the bass, and here's the mid-range, right? And so it goes through here. I'm sorry. Here's the volume. It goes through here, and it goes on to the grid of the second half of the first preamp 12AX7, right? And it comes out to the plate, and it goes through here. Here's the next coupling capacitor, and there you see the next resistor in the Opto-Coupler, OC2. So here's the LED. If that LED is off, the signal will be prevented from flowing out to the signal of the amplifier. So that is basically how these optocouplers work. But what's very interesting is, what about the circuitry that controls these LEDs, right? Now that's tied to the switching mechanism down here. And as it turns out, they're just on one big loop. So over here, down here in the switching mechanism, we essentially have two circuits here where you have some low voltage coming off of the switching mechanism. This is very low voltage. You don't need a lot of voltage to turn these LEDs on. And if this circuit is on right here, you can see that it comes up here and it turns off. It'll turn on, I'm sorry, the LED. Comes over here, it turns on this LED. So the circuit passes through both LEDs. Then it comes back over here, and it dumps off to this -10 DC volts, right? And if you look closely, it looks like it's a complete loop, and it kind of is, because look, it's just that same LED circuit is coming back down here and going through the LED of the Opto-Coupler in the dirty circuit. Now, why is it that you could have this complete loop like this? Because if you turn on the voltage and come all the way through here, you would think that, well, wait a minute, I'm turning on all Opto-Couplers. But no. Look at the directionality of the Opto-Couplers. This one, if you look at the directionality of the diode, which means that the voltage only flows this way, you can see that it's pointed. This is the negative side, called the cathode. This is the positive side, the anode. You can see that it's set up so that the voltage can go this way. The voltage cannot go the other way through this diode. And by the way, diodes are also used in the newer amps as rectifiers for turning AC into DC voltage. It's the same sort of thing. So it comes down this way. You've got the voltage coming down this way. Now look over here, and you can see that the Opto-Coupler's LED diode is actually facing the opposite direction, right? So when the voltage comes down this way, it can't go this way. It's prevented from going this way, and vice versa. When you've got voltage coming over here, it's prevented from going this way into the LED, through the LED of the clean circuit. So you've essentially got two circuits here with the voltage kind of going in different directions in a way that they bump into each other and they dump off here. And as you can see, I put a little notation here, 42. That's a test point that I created to make sure that in either case I was getting this -10 volts at this moment in the circuit, which I was. So that's essentially how this works. You've got this loop, comes up here, goes around here, comes back and goes over here, and then it actually comes, where it says -10, it comes back over here and dumps down and goes around again. It's just a basic loop. Now the same is true, like that's when the clean channel is on. But when the dirty channel is on, you go over here and here's the loop. And it comes up here, goes around here, so it goes through this Opto-Coupler, which either permits or prevents the signal from coming out and going out to the rest of the amplifier. It comes down this way, goes through this Opto-Coupler, which does the same thing. And then it comes back up to this same part of the circuit and then dumps off and goes around again. So you basically just have these two loops, and these Opto-Couplers, you're turning them on or you're turning them off in order to see if they, in order to permit or prevent signal from getting through one or the other circuit. So just a really interesting design and an interesting use of solid-state technology in an amplifier of this nature. So, could this be the problem? Remember, I said that there was a problem with clean and dirty. I wasn't sure if maybe the clean and dirty switch was broken or something else was going on, because I was getting some sound out of the dirty circuit and no sound out of the clean circuit. It made me wonder whether maybe one of these guys was fried in a way that the LED couldn't illuminate, and therefore the resistance couldn't drop, therefore the signal couldn't get through the circuit. I wasn't sure. And so I had to figure out a way to test these guys. Now, I could have tested them by taking them out of the circuit altogether, like just clipping their leads, taking them out, desoldering them, or something like that, and testing them on my multimeter to see what sort of resistance I get. One of the problems is that you can't really test resistance of resistors, this side of it, in circuit. That's a problem. You're going to get an inaccurate reading no matter what you're using to measure a resistor when it's in circuit. So I had to find a way to figure out whether or not this diode, when it lights up, was adjusting the resistance of these resistors in each of these optocouplers. So how do you do that? How do you work on these optocouplers, especially when you don't want all the high voltage going through the amp? You just want to sort of test them individually to see whether or not they are the source of your trouble. So I went on to the Tektronix forum, where a bunch of oscilloscope enthusiasts and old Tektronix engineers hang out, and I asked them some questions, and they came up with a very clever device that I should use to test these optocouplers. And that device is right here. Okay, this is a 9-volt battery, and as you can see, I have one lead. Let me just move this over. I have one lead coming off the negative terminal of the battery, 9-volt battery, and I have another lead coming off the positive terminal, and then I have a little wire for touching to the different test points in my circuit. Now, what's the purpose of this device? The purpose of this device is to actually energize each of these optocouplers individually and then see what impact that has on the resistance. Sorry for the barking dog in the background. I have two dogs and they're playing with each other. One's trying to get the other one to wrestle. All right, so here we go. We've got these two leads set up in such a way that I can actually energize the LED and then monitor what impact it has on the resistance with my multimeter. Now again, measuring resistors in circuit is problematic because there are other things around the resistors that may impact your reading. But what I'm just looking for is, hey, if I energize the LED, does it do anything? Does it have any impact on the resistance? Because if it does, it's probably an indication that it works. All right, so one thing you have to do is you have to be very careful when you're connecting a 9-volt battery to an LED like this. Remember I said earlier, it's very low voltage. We're talking about, under 10 volts that's going through the LED part of the circuit. So yeah, I have a 9-volt battery, but the current coming off this battery is enough to fry any LED. So what I've done is, inside this heat shrink tubing is a 1K resistor. And that 1K resistor basically throttles down the current enough such that the LED won't fry. So that's my test rig, and I'm just going to keep this in the drawer of my bench for any time that I have to energize anything, for that matter, to test an individual component in circuit and to determine whether or not it might be failing. So next, let's go ahead and take this clever little device that these guys from the Tektronix forum taught me how to build and apply it to an optocoupler and see what impact it has on the resistors of those optocouplers. Okay, so here we are. We're sort of set up and ready to go with our test. I've picked this particular Vactrol optocoupler to test for our little experiment. And you can see that I have my multimeter already set up here, and it's set to ohms. Now, in another video that I'll be making, you should pay close attention to which multimeters you use to test your amplifiers. I learned the hard way that you can't use just any multimeter. There's actually some specifications of the multimeters that make some of them better suited to testing amps than others. It's a subject for another video, but in the course of testing this amplifier, I discovered that my other multimeter was actually ill-equipped for a variety of reasons. Now, as you can see, what I've done here is I've got the negative lead connected to, it doesn't matter really for the resistance. You can test, resistors have no polarity here, so I can test the resistance in either direction, and I've got the one lead coming out of the multimeter connected to one side of the resistor and the other lead connected to the other. This is the resistor side of the Vactrol, and this is the other side. There's two leads on this side and there's two leads on this side. This is the photocell side, or what we call the LED side. And I've got the negative lead connected to the cathode of the LED. Now, you may not be able to see it right now. I'll see if I can shine another light on it real quickly. But right there, I don't know if you can see the little positive sign, right in there. That positive sign is, you can see it on the circuit board next to each of the optocouplers. That is indicating where the anode of the LED is. And so if you have four corners here, the anode is down here of the LED, and that's the cathode. So that's why I'm connected to the negative. So in order to do my test, pretty straightforward here. All I have to do, I've got this negative clip is connected to the negative of my Duracell battery here, my 9-volt battery. All I have to do is touch this little guy to the multimeter. I'm sorry, to the anode, and see what happens over here in terms of the resistance that's going that it's measuring on the resistor side. So let's go ahead and do that and look at the resistance. It's dropping down. It's now about 1.84K. Let's take it off. And it's back up to 470K or so. Let's put it on. Basically what we're doing is we're illuminating the LED inside the Opto-Coupler. You can't see it because it's inside. The resistance goes down. Take that off. Now the LED is going dark. That's why it's climbing here. It's essentially turning itself off, and the resistance is climbing. Isn't that amazing? So cool. And I'm doing all of this, by the way, as you can tell, the amp is not powered up. I'm just doing it with this little 9-volt battery. So this is a really neat way to test these guys in circuit. It's just working just fine. I love it. Now, one of the things I'm doing here, and I just want to impress upon everybody, is even though this amp is off, and by the way, this amp automatically discharges all of its electrolytic capacitors to prevent any chance of getting shocked, but even though this amp is off and it's unplugged, I'm still practicing really good safety best practices here. I have one hand in the amp. I have another hand in my pocket, which is always a good way to make sure that you can't pass voltage from one hand to the other through your heart. I'm also using these clip-on leads for my multimeter. That's what allows me to just use one hand. If I can get everything kind of clipped on so that I only need one hand to do the rest of the work, for example, touch this guy right here, boom, right? There's really no way for me to get shocked. Now, I can't get shocked anyway because we're just using a 9-volt battery, but even so, why not practice your best practices all the time? That way you habitually are always going to be safe and keep yourself from getting injured. So that's pretty much it. This is a very clever little device, this 9-volt device. I'll keep it on my bench. And, if you have questions, put them on the the comments below the video. By the way, make sure you look at the comments anyway, because I invariably leave some important detail out, and I will update the video or the comments to address anything that I left out. And then one other question I'm sure everybody has is, well, why don't you do this with the amp powered up? Like, what happens if you power the amp up and then do the same exact test? And the answer is, I did do that. Like, you know, I did power the amp up and watched very carefully as I switched the circuit on and off with the clean and dirty button to see how the different opto-couplers behaved. And for the most part, I discovered that they're all working properly, but it did lead me to find one of the actual problems with this amp, which was that I found that there was missing voltage somewhere, and it was tied to a problem way over on the right side with the header that comes off of the transformer and supplies voltage to that circuit. Anyway, that's for the other video about this amplifier, which will be posted relatively soon. Now you know what an opto-coupler does, how it works, and a really easy way of testing it. Thanks very much. GoPro, stop recording.